Okay, so the intensity of electromagnetic radiation received by the detector after passing through a thickness x of blood is given by I equals I zero e to the minus mu x, where I noted the intensity of that would have been received if the blood were not present, and mu is the attenuation coefficient of blood. The red LED emits visible light of wavelength 650 nanometers, and infrared emits a wavelength of 950. So what I've done is for red light, um, we know that the wavelength is 650. So I've gone to the graph. I've drawn a line vertically upwards from 650 and also at 950. That's for infrared rays. I've drawn a line vertically up from 950 as well. Now you got one line here that represents the deoxygenated blood, and the other line represents the oxygenated blood. And this is the link between wavelength and the attenuation coefficient. So the graph shows how the attenuation coefficient varies with wavelengths for oxygenated and deoxygenated blood. So I've drawn these horizontal lines at where this vertical line meets each line for deoxygenated and oxygenated, and I've just gone across, and I may need them for later on. So what you have to note is this is a logarithmic scale. So each gap, as you can see, is getting smaller and smaller. So the easy way to look at this is that you got 10 and 100, and between 10 and 100, we've got 9 jumps, and each jump is worth 10. So it'll be 10, 20, 30, 40, 50, 60, all the way to 100, and then the next gap is 100 to 1000. So the jumps are 100, 200, 300, 400, 500, 600, and the next gap is 1000 to 10,000, and then that's 1000, 2000, 3000, 4000, and so on and so on. Okay, so the question is, we know the initial intensity, which is 1.8, and we want to work out the intensity when infrared passes through 1.4 millimeters of oxygenated blood. Now, we've got the expression that we've got from the beginning of the question that links intensity with all the three variables. Now, in this question, we have got the intensity here, the initial intensity. We've been given the distance of 1.4 millimeters, and we want to find mu. And if you read carefully, it says for infrared and oxygenated blood. So all I'm going to do is, I know this was the line for infrared, and I'm going to go across to oxygenated blood, or go right across there. That's in between 100 and 200. And I know it's a kind of a logarithmic scale, so I'm going to make a rough estimate. That's halfway between, let's say, 100 and 200. So that's 150 meters to the minus 1. So that was 950 because it's infrared. Going to oxygenated blood, and that's the line at the top, and going across, that's between 100 and 200, so that's about 150. So that's 150 meters to the minus 1, and I see that's meters to the minus 1, that's millimeters, so therefore I'm going to put that into meters. So these two should multiply to give you zero, no unit. So meters to the minus 1 multiplied by meters cancels out. So I multiply it all up, put it into the formula. We've got 1.8 as the initial intensity. We've now got mu from the graph. We've got the distance uh, passing through of how much blood. So we got X, and we converted into meters, and we've got an intensity drop of 1.46 watts per meter squared. The second question talks about an oximeter. So an oximeter determines the fraction of radiation transmitted at each wavelength. So all we do is we just rearrange this equation to get I over I zero, and what we see it's equal to e to the minus mu x. Okay, now it says deduce whether I over I0 will be smaller for red or for infrared radiation if blood is deoxygenated. Okay, so what we've got to do is we've got to look at this expression, and we're still assuming that it's passing through 1.4 millimeters of oxygenated blood. There's no other data to suggest otherwise. So we know that mu varies for infrared and red. So all I'm doing is I'm going to go up. And for infrared, I'm going to go up to deoxygenated blood and I come across, and that's 80 meters to the minus one. And for red, I'm going to go up and deoxygenated blood, that's 400 meters to the minus one. So I've written that here. For red, deoxygenated blood, mu is 400 meters to the minus one. For infrared, deoxygenated blood is 80 meters to the minus one. I'm going to pop that into this expression because it wants to know which one is smaller. Is it for the red or for infrared? So e to the minus 400 times by x, which was 1.4 times 10 to the minus 3, as it's passing through 1.4 millimeter of oxygenated blood. And we get a fraction of 0.57. And we'll repeat that for infrared and deoxygenated blood, which was 80 as we saw from the graph, and then put that in, and we got 0.89. And we clearly see that now that's going to equal I over I0, the fractional change of the intensity. So the fractional change of the intensity is smaller for the red compared to the infrared for deoxygenated blood.